Namaste, welcome back to the session of basic thermodynamics. In the previous session, we have gone through few of the fractions such as the mass fraction, mole fraction and volume fraction. Now I will continue with the few of the equations. Very first equation is expression for gas constant, which is denoted by R. We know for an ideal gas PV is equal to mRT is the ideal gas equation, and I have not written any suffixes over here because of that equation is for the mixture. Now the same equation can be written for various constituent gases, wherein for constituent gas A the pressure is the ideal gas equation is PAV, which is equal to MARAT, and for constituent gas B PBV, which is equal to MBRB times of T, PCV, which is equal to MCRC into T for constituent gas C. So these are the equations for constituent gases A, B, C respectively. Here one thing is for sure, we need to observe that V and T for mixture and V and T for constituent gases will remain constant. What I mean to say is volume and temperature of the mixture as well as volume and temperature of individual constituent gases are same. Now from the Dalton's partial pressure law, I know the overall pressure of the mixture is equal to summation of partial pressures of individual constituent gases when both are at same volume and temperature. So this is what is the law. P is equal to PA plus PB plus PC when V and T are constant for both mixture as well as for individual constituent gases. So from these equations V and T are constants, so that I can replace P from each of the equation into this equation. So if I solve the P for mixture, the P takes this form M into R into T divided by V. For PA, MARA T divided by V, and for PB, MBRB T divided by V, and PC, MCRC T divided by V. If I look onto the equation, T and V are constant, so that I can eliminate T and V from all the individual terms, so that I will be left out with M into R, which is equal to MARA plus MBRB plus MCRC. Here on the left hand side I have M, I will send this M onto the right hand side, so that MA by M into RA plus MB by M into RB plus MC by M into RC. So that finally the R, the equation for R takes this form, wherein MA by M can be written as MFA times of RA, MB by M is MFB times of RB, and MC by M is MFC times of RC. Here MA by M is nothing but the mass fraction of constituent gas A, MB by M mass fraction of constituent gas B, MC by M mass fraction of constituent gas C. If you look onto the equation, it looks like this: R is equal to RA plus RB plus RC. Not only that, along with individual terms, you need to multiply their corresponding mass fractions: RC, MFC, RB, MFB, RA, MFA. So this equation is the equation in order to find the gas constant for the mixture. If you look onto this, mixture's gas constant is totally dependent on individual constituent gases gas constants. If you are aware of RA, RB, RC, then you can easily extract the value of R for the mixture. So this is the main equation that I need to remember in order to calculate the R for the given mixture. Okay, let us look onto the next equation. Next equation or next expression is with respect to the molecular weight. Molecular weight is denoted by capital M. We knew that the equation for universal gas constant R bar is given by molecular weight of the substance into its gas constant M into R. So from this equation I will solve the equation for R. R is nothing but gas constant. R is equal to R bar divided by M. Since I have not written any suffixes over here, this is the equation for mixture of various ideal gases. Next, I will write the same equation for individual constituent gases. RA is equal to R bar by MA, RB is equal to R bar divided by MB, RC is equal to R bar divided by MC. These are the equations for constituent gases. So R bar is the universal gas constant, which will not change even for the mixture or for the individual constituent gases. So now from previous equation what we have derived, I have equation for R for the mixture. R is equal to MFA times of RA plus MFB times of RB plus MFC times of RC. Now I have expressed R in various forms, R for the mixture and R for the individual constituent gases. I will substitute all these things into this equation. R bar by M, which is equal to MFA. RA is written as R bar divided by MA plus MFB. RB is written as R bar divided by MB plus MFC. RC is written as R bar divided by MC. If you look onto the equation, in the numerator R bar is common, so that I have eliminated R bar. Now I am left out with 1 by M, which is equal to MFA by MA plus MFB by MB plus MFC by MC. Make sure here MFA is the mass fraction of A, capital MA is the molecular weight of A, MFB mass fraction of B, molecular weight of B, mass fraction of C and molecular weight of C. So now if you solve the equation for M, the equation takes this form. So here M, I have not written any suffix over there. This M stands for molecular weight of the mixture. If you need molecular weight of the mixture, then you should make use of this final form. So this is one such expression to find the molecular weight of given mixture. The same molecular weight of the mixture can also be found by making use of the other expression. I have written that over here. The name is alternate form for M, I mean alternate expression for molecular weight of the mixture. We were aware that mass of the substance can be given by number of mole of the substance into molecular weight of that substance. So N into M can give us the small m, which is nothing but mass. This is for the mixture, because I have not written any suffixes over there. If I write the same equation for various constituent gases, then Ma, which is equal to Na Ma, please make sure Ma mass of constituent gas A, Na number of moles of A, capital Ma molecular weight of A. Similarly, Mb is equal to Nb Mb and Mc is equal to Nc times of Mc. From very base equation we have mass of the mixture, I mean mass of the various constituent gases mixture is equal to summation of individual constituent gases masses, that is M is equal to Ma plus Mb plus Mc. Now if you look here, you have equation for all the terms. M is Nm, Ma is Na into Ma, similarly Mb is Nb into Mb, Mc is Nc into Mc. Now N, the term which is nothing but N, which is on the left hand side, please send that onto the right hand side, so that on the left hand side I will be left out with M and I will send this N onto the right hand side. So that right hand side equation becomes Na by N into Ma plus Nb by N into Mb plus Nc by N into Mc, where Na by N is nothing but the mole fraction, and I have denoted mole fraction of constituent gas A by Xa times of Ma. Similarly, Nb by N mole fraction of B, that is Xb times of Mb plus Nc by N mole fraction of C into Mc, so that your molecular weight of the mixture will become mole fraction of constituent gas A into its molecular weight plus mole fraction of constituent gas B into its molecular weight plus mole fraction of constituent gas C into its molecular weight. Here also the equation looks like very similar to that of the R equation. M is Ma plus Mb plus Mc, but you need to multiply corresponding mole fractions with that constituent, that is Xama plus Xbmb plus Xcmc. That is what is the mole fraction of the mixture in the alternate form. Here I have denoted Xa, Xb, Xc as the mole fraction. You can also write mole fraction denotion as a MLF, where ML stands for mole, F stands for fraction. Mole fraction of A, mole fraction of B, mole fraction of C. The giving the notation process, it is up to you. You can denote the mole fraction by X, or else you can denote the mole fraction by MLF also. So now we have two different forms for molecular weight of the mixture. One form is related with mass fraction, another form is related with mole fraction. Whenever in the problem, if they are specifying the mass fraction, then you need to make use of this formula for molecular weight of the mixture. Whenever they are dealing with the mole fraction, in order to find the molecular weight of the mixture, please make use of this equation, so that we are very aware of both the forms of the equation for molecular weight of mixture, that is in terms of mass fraction as well as in terms of mole fraction. Okay, let us look on to the next set of equations. Here I will be looking for the expression of Cv, where Cv is the specific heat of the given mixture of the gases at constant volume. In order to arrive into this equation, I need to look for a base equation, which is nothing but the internal energy equation. Internal energy equation says that internal energy of the mixture of gases will be equal to summation of internal energy of that of constituent gases. That is, U for mixture will be equal to UA plus UB plus UC of that of constituent gases. This U is an extensive property because I have written U in capital letter. If I want a specific property, then small u is equal to U divided by M. I mean, capital U divided by M will give us the small u, so that I can get intensive property, which is nothing but U. By making use of this, capital U can be written as small u into M. So, U into M, similarly MA into UA, UB into MB and UC into MC. That is the summation. Next, differentiate this entire equation with respect to T. Here one thing we need to observe, that is the entire mixture's volume and individual constituents volume, as well as entire mixture's temperature and individual constituent temperatures are same. Volume and temperature for mixture as well as for individual constituent gases are same. By keeping that in mind, I am differentiating entire equation with respect to the temperature. So, M will be the mass will not vary, and U, internal energy, will vary with respect to the temperature. So, du divided by dt. Similarly, Ma dUA divided by dt plus Mb dUB divided by dt plus Mc dUc divided by dt. What I mean to say is, internal energy is getting differentiated with respect to the temperature. So, now dt is nothing but the difference in temperature for the mixture and difference in temperature for the constituent gases are same. Because of that, I have eliminated difference in temperature dt. Next, I have written the expression for du. Make sure it is a specific property. M I have written as it is. Small du can be written as Cv into dt. In the same way, Ma I have written as it is. dUA can be written as Cv of A into dt plus Mb dUB is Cv of B into dt plus Mc dUc is nothing but Cv of C into dt. Again, in this stage, dt, difference in temperature for the mixture as well as difference in temperature for individual constituent gases is same. I will eliminate the dt one more time, so that I will be left out with Mcv, MaCva, MbCvB, McCvC. Now, I will take M onto the right hand side, so that Cv is equal to Ma by M Cva plus Mb by M Cvb plus Mc by M Cvc. I know Ma by M, which is nothing but the mass fraction of constituent gas A, Mb by M mass fraction of constituent gas B, Mc by M mass fraction of constituent gas C. If I look onto the final equation, Cv, I do not have any suffix of constituent gases. Cv is for the mixture. Cv of the mixture is Mfa times of Cva plus Mfb times of Cvp plus Mfc times of Cvc. What I mean to say is, if you want the mixture's specific constant, I mean specific heat at constant volume, then it is a summation of products of mass fractions into corresponding constituent gases specific heat. That is what is the equation to you. Cv is Mfa Cva plus Mfb Cvb and Mfc Cvc. So, that is what is the Cv equation. Make sure in order to arrive into the Cv equation, you need to begin your expression from internal energy equation. Next, I will move on to the expression for Cp. Here it was a Cv, here it is Cp, where Cp stands for specific heat at constant pressure. In order to arrive into this equation, I need to begin the expression with H is equal to Ha plus Hp plus Hc, where H is the enthalpy. Here I do not have any suffix, that means H of the mixture is equal to summation of H of that of individual constituent gases. Now, this is a extensive property, because of that I have written it in capital letter. If I need the specific property, please divide that extensive property divided by mass, so that you will get the intensive property, which is nothing but small h. So, now capital H is nothing but small h into M. So, H is M into H, which is equal to MaHa plus MbHb plus McHc. Again, differentiate the above equation with respect to the T, because T and V for both mixture as well as for constituent gases are same. So, that upon differentiation, M is a constant dH by T dt, which is equal to MA dHA by dt plus MB dHB by dt plus MC dHC by dt. Since the difference in temperature for all the for all the constituent gases as well as for the mixture is same, I will eliminate the dt. I will be left out with M and equation of dH. dH is nothing but Cp into dt, which is equal to MA dHA is Cpa into dt plus MB dHB Cpb into dt plus MC Cpc into dt. Again, temperature for mixture as well as the constituent gases is same. I will eliminate dt one more time. I will be left out with Cp, which is equal to MA. I will send this M on to the right hand side. MA by M Cpa plus MB by M Cpp plus MC by M Cpc. Now, MA by M, MB by M, MC by M are nothing but the mass fractions of individual constituent gases. So that your final equation for Cp becomes Cp is equal to MFA Cpa plus MFB Cpb plus MFC Cpc. Here also it is very similar equation to that of the Cv. Mass fraction into corresponding gases specific heat at constant pressure. What I mean to say is, the Cp of the mixture, specific heat at the constant pressure of that of mixture is nothing but the summation of product of mass fraction and specific heat of corresponding individual gases. So that is what is the expression for Cp. In order to arrive into the Cp, you need to begin your equation, you need to begin your solution from the equation of H. And the last expression is expression for change in entropy. Here I will be beginning the equation with the same term, which is nothing but entropy of the mixture will be equal to summation of entropies of individual constituent gases. Since I have written capital S, it is an extensive one. If I have to make it an intensive, then please divide capital S by M so that you will get small s. Small s is an intensive property, capital S is extensive property. If I want capital S, it is nothing but M into small s. That is what I have written here, M into S, which is equal to MASA plus MBSB plus MCSC. Again, I knew temperature and volumes are constant. I will take one of that equation. I will differentiate entire equation with respect to the constant temperature T. Upon differentiation, I cannot differentiate mass. So, mass into change in entropy divided by change in temperature, which will be equal to MA dSA by dt plus MB dSB by dt plus MC dSC by dt. I know change in the temperature for mixture as well as the individual constituent gases is same. Because of that, I will eliminate dt. Hence, I will be left out with M into ds, which will be equal to MA dSA plus MB dSB plus MC dSC. Again, the same step. Please send M on to the right hand side so that ds is equal to MA by M into dSA plus MB by M dSB plus MC by M dSC. Where MA by M is nothing but mass fraction of A, MB by M is nothing but mass fraction of B, MC by M is nothing but mass fraction of C. So that the change in entropy of the mixture will be equal to summation of product of individual constituent gases mass fraction into its change in entropy. So ds is equal to MFA dSA plus MFB dSB plus MFC dSC. If you look on all the three equations, it looks very similar to one another, wherein mass fraction and corresponding property of that of constituent gas summation is present. Please observe all the three equations, they have the same form. So these are the few expressions that I will be making use while solving the problems in order to find various properties of mixture as well as various properties of such of constituent gases. Okay, let us look onto the final expression. We have certain thing to prove over here. The proof is like this. The ratio of partial pressures will be equal to the ratio of mole fraction will be equal to the ratio of volume fraction. I will write the final form here itself. I will take P by P, wherein the numerator is partial pressure of constituent gas A and the denominator is partial pressure of the mixture. And here also number of moles of A divided by overall number of moles of the mixture. Here also volume of constituent gas A divided by volume of overall mixture V. So I need to prove this. These ratios are equal. That is nothing but the proof. I need to prove this. So because of that, what I have done is I have taken the base equation, which is nothing but PV is equal to M into R into T. Now PV is equal to m, mass can be written as n into m. This is nothing but small m, and R into T. In the next stage, I will write PV is equal to m into R is nothing but the equation for universal gas constant. So m into R is written as R bar, and I have written n as it is and T as it is. So that this is the one form of equation, and I will call this equation as the first equation, and this is for the mixture because I have not written any suffixes over there. Next, for the individual constituent gases, if I write the same equation, PAV which is equal to NA R bar T. Here I have written suffixes for P and Na because I knew volume and temperature of mixture as well as of constituent gases are same. Because of that, I have kept V and T as it is for mixture as well as for a constituent gas. Next, R bar is nothing but the universal gas constant. It is universal. Because of that, it is a same thing for mixture as well as a constituent gas. In the next step, what you have to do is you need to take a ratio of these two things. I mean, I have written equation number 2 for the constituent gas, equation number 1 for the mixture. I will take this into consideration, 2 divided by 1. 2 is nothing but PAV into which is equal to Na R bar T divided by PV which is equal to N R bar T. If you look onto the terms, volume will go off, R bar will go off, temperature will go off. You will be remained with PA by P which is equal to Na by N. So this is the equality that I am going to get by considering one such form. Next, I will do the same thing over here. Again, I have PV is equal to N R bar T for the mixture that I have derived over here. I am taking this equation again. PV is equal to N R bar T, where P is pressure, V is volume, N is number of moles, R bar is universal gas constant, and T is temperature. Now, in the previous stage, I have kept P as a variable, PA, P, and I have kept V as constant thing. Here, Dalton's partial pressure law is the law on which I have taken pressure as the variable. In the second stage, I will keep pressure and temperatures as constants, and I will make V as the variable. When V becomes the variable, when you are dealing with Amagat's law of additive volume. What does that law says? Overall volume of the mixture will be equal to summation of volume of individual constituent gases when pressure and temperatures are constant. By keeping that law in mind, I have written this equation wherein P into VA which is equal to Na R bar T, where P and T are constants and VA is nothing but the volume of constituent gas A, Na is nothing but number of moles of constituent gas A. So now I will call this as the equation number 2 and this as equation number 1. Again, 2 divided by 1 is my consideration, PVA divided by PV which is equal to Na R bar T divided by N R bar T. So now P by P will go off, R bar T will go off. I will be remained with VA by V which is equal to Na by N. So VA by V is also equal to Na by N. From the previous expression, PA by P which is also equal to Na by N. If I combine these two, please look onto these two. Na by N is common. Next, PA by P which is equal to VA by V. If I merge these two equations, I will come across this equation, PA by P which is equal to VA by V which is equal to Na by N, wherein PA by P which is equal to VA by V can be written as volume fraction of A, and Na by N is nothing but mole fraction of A. Here the A, suffix A stands for constituent gas A. If you have constituent gas B, a different gas, the same expression goes like this, PB divided by overall pressure which will be equal to volume fraction of B which is also equal to mole fraction of B. So this is the equation for constituent gas B. The same equation will go for multiple constituent gases. So this is what is the proof that I was expecting at the beginning. PA by P which is equal to Na by N which is equal to VA by V, or PB by P which is equal to NB by N which is equal to VB by V. So at the end you need to be very aware PA by P can also be written as volume fraction of A which is also written as mole fraction of A. This equation helps us a lot while calculating the variables while solving the problems. So this is what is the last concept of theory of mixture of ideal gases. Now whatever the equations that we have derived, by making use of them, I will be going through the problems. So let us look onto few problems. Okay, let us look onto the problem and then try to solve the various variables. What I have done over here is I have taken a problem wherein I will keep all the things as a variables, so that I can make use of whatever the equations that I have derived in order to find the variables. In a single problem, I will keep more and more variables, so that I can come to know how to solve the problem with the given data. Now I will read out the problem to you. A mixture of gases contains 1 kg of carbon dioxide and 1.5 kgs of nitrogen. The pressure and temperature of the mixture are 3.5 bar and 27 degrees Celsius. So this is the given data to us. We have mixture of ideal gases. This mixture has two constituent gases such as carbon dioxide and nitrogen, and the entire mixture's pressure and temperature are known to us. Pressure of the mixture is 3.5 bar and temperature of the mixture is 27 degrees Celsius. By keeping these two values, we need to calculate whatever the things we have derived now. First thing is, as soon as the problem is given to you, you need to decide the gases. In order to ease out the writing phenomenon, I will decide CO2 as the constituent gas A and N2 as constituent gas B. Next, I will go through molecular weights of constituent gases. Molecular weight of molecular weight of CO2 will come around 44, molecular weight of N2 will come around 28. Next, I have mass of CO2, CO2 is 1 kg, Ma is 1 kg, mass of N2 is 1.5 kg. If I summate those two, I will get mass of the mixture. Mass of the mixture is nothing but 2.5 kg. Individual gases masses addition will give me the mass of the overall mixture. In the same fashion, I can calculate number of moles of the individual constituent gases. Na is the number of moles of constituent gas A. A is nothing but carbon dioxide. Nb is nothing but number of moles of constituent gas B. B is nothing but nitrogen. Na is nothing but Ma by molecular weight, Mb by molecular weight. If I substitute the formulas, I will get these two values. These two values are nothing but the constituent gases number of moles. If I add these two things, then that becomes total number of moles of that of mixture. So N is equal to Na plus Nb. I have N for the mixture, I have total mass for the mixture. By making use of these two, I am going for the first set of unknowns, which is nothing but mass fractions of individual constituent gases. Mass fraction of A is nothing but Ma by M. You have calculated all the values. While substitution, upon substitution, you will get the mass fraction of A as 0.4. Mass fraction of B, which is nothing but Mb by M, which is equal to 1.5 by 2.5, you will get 0.6. While dealing with the theory, one aspect we have come to know that upon adding whatever fractions we have derived, that fraction addition should give us the unity. Please look onto these two. 0.4 plus 0.6, I will get unity. That means my answer is correct. Next, I will look for mole fractions of individual constituent gases. Mole fraction of A is nothing but Na by N. Mole fraction of B is nothing but Nb by N. All these values Na, Nb, N we have calculated over here. Upon substitution, I will get mole fraction of A as 0.2978 and mole fraction of B as 0.7022. Upon adding these two, I have to get 1 because these two are the fractions. Whether you add mass fraction or whether you add mole fraction, addition of those fractions should be equal to unity. Upon adding these two, I will get unity. Upon adding these two also, I will get unity. So that is what is the fractions speciality. Now I will look on to the partial pressures. Those are the variables to me now. Partial pressures of individual gases. The gases are nothing but CO2 and N2. From the previous proof, what I have done, I know Pa by P is also equal to mole fraction of A, which is also equal to mole fraction, volume fraction of A. I will take these two, Pa by P. P is given to us 3.5 bar, which is equal to mole fraction of A. You have calculated mole fraction of A as 0.2978. Upon multiplying these two, you will get partial pressure of constituent gas A, which is nothing but CO2. So partial pressure of A is nothing but 1.0423 bar. What do you mean by this partial pressure of A? The CO2 is exerting this much amount of pressure. Next, if you want partial pressure of another gas, which is nothing but N2, then you need to make use of the Dalton's partial pressure law. which says that P is equal to PA plus PB. You are aware of overall pressure of the mixture, which is nothing but 3.5 bar. PA you have calculated and only unknown is PB. Upon manipulating this, you have got PB as 2.4577 bar. So now you have partial pressures of individual constituent gases. PA is this much and PB is this much. So these two are the partial pressures of the given gases, which are nothing but CO2 and N2. Next variable to me is R for the mixture. R is nothing but gas constant for the mixture. I have derived this equation. Gas constant of the mixture is nothing but MFA RA plus MFB RB. You are aware of mass fractions of A and B, but you are not aware of RA and RB, where RA and RB are nothing but gas constant of constituent gas A and gas constant of constituent gas B. Initially you need to find RA and RB. For RA I have formula R bar divided by molecular weight of A, RB R bar divided by molecular weight of B. You are aware of molecular weight of A and B, you have calculated as 44 and 28, and R bar is nothing but the universal gas constant. 8.314 divided by 44 will give us the R for constituent gas A, 8.314 divided by 28 will give us the R for constituent gas B. By taking those two values, upon substituting in this equation, I will get R. This R is nothing but gas constant of mixture of ideal gases, which is nothing but 0.2537 kilojoules per kg Kelvin. Now all the variables in this equation are found. MFA is known, RA is also known, MFB is known, RB is also known. Now I have overall mixtures gas constant. By making use of this, I can get molecular weight of the mixture also. In the initial stage, you have calculated molecular weight of constituent gases A and B. In this stage, you will calculate molecular weight of entire mixture. I know R bar can be written as M into R. Now I am looking for molecular weight. Molecular weight is nothing but R bar divided by R, where R bar is the universal gas constant 8.314 divided by capital R is nothing but 0.2537 that you have calculated from the previous step. Upon doing this, molecular weight of the mixture will come around 32.77 kg per kg mole. Make sure the molecular weight of the mixture is 32.77 kg per kg mole, whereas molecular weight of the individual constituent gases are 44 and 28. So this is how, by taking a single problem, I can calculate almost all the variables that I have come across. All the equations we have derived, please make use of those equations in order to go through the individual unknowns. So this is what is the problem which explains maximum number of unknowns to you. So this is what is for this session. Until then, namaste.